Swayam Prabha. Digital India. Educated India.
In this lesson, we will consider the implications of reciprocity in resistive networks. We have stated reciprocity and also derived it in terms of two-port parameters, but two-port parameters really refer to ratios of some electrical quantity to some other electrical quantity under certain conditions. Okay. So, we can talk about reciprocity even without talking about any particular two-port parameter set. Okay. So, in this lesson, we will look at what reciprocity in terms of each of the two-port parameters implies and also how it is useful. Okay. So, let us first take y parameters. Reciprocity says that y12 equals y21. Okay. So, if I have a resistive network and two ports, what does it mean? So, let us say I connect V1 to the first side and short circuit the second side. The current here would be by definition y21 times V1. Okay. On the other hand, if I connect V2 hat to the second port, short circuit the first port, the current here would be I1 hat, which is equal to y12 times V2 hat. And by the way, let me define this current as I2. Okay. So, in this form, in terms of y parameters, it says that the ratio of short circuit current in one port to the applied voltage is the same as the short circuit current in port 1 to the voltage applied at port 2. Okay. So, this what it implies is short circuit current in port 2, ratio of that to the voltage applied at port 1, this is y21 will be equal to I1 hat divided by V2 hat. Okay. The reason I am pointing this out is different two port parameters have different implications in terms of exactly what you are measuring, and also in different circumstances you will have ratios of voltages or currents or voltages across open circuits and currents through short circuits and so on. So, you should be able to use reciprocity for all those situations. Okay. Reciprocity means ratio of short circuit current in port 2 to the applied voltage at port 1 equals ratio of short circuit current in port 1 to the applied voltage at port 2. Okay. Now, this is of course true for purely resistive networks. Okay. So, this is one particular statement of reciprocity in terms of short circuit currents. Now, similarly, let us say what it means in terms of Z parameters, which says Z12 equals Z21. So, when you are measuring Z21, you will apply a current to port 1 and measure the open circuit voltage at port 2, and when you are measuring Z12, you will apply a current to port 2 and measure the open circuit voltage at port 1. And this statement of reciprocity means that V 2 by I 1 equals V 1 hat by I 2 hat. Okay. So, here the ratio of open circuit voltage to the applied current is the same whether you apply the current at port 1 and measure the voltage at port 2, or you apply the current at port 2 and measure the current at port 1. Okay. And if we do it with H parameters, we will have H 1 2 equals H 2 1, and this is my resistive 2 port. Okay. When you are measuring H 2 1, you will apply a current to port 1, terminate port 2 with a short circuit and measure the current in port 2. And when you are measuring H 1 2, you will apply a voltage to port 2 and have an open circuit across port 1 and measure the voltage across that open circuit. Okay. This of course implies that I 2 by I 1 equals minus V 1 hat by V 2 hat. Okay. So, basically the current gain from port 1 to port 2, which is what is given by this, is the negative of the voltage gain from port 2 to port 1. So, you get this negative sign if you choose the direction of currents as shown here. If you had chosen the current to be in the opposite direction, you won't get that, but we always choose the current directions consistent with the 2 port parameter definitions. Okay. So, we get this I 2 by I 1 to be minus V 1 hat by V 2 hat. Okay. And with G parameters, we have exactly the same thing. G 1 2 is minus G 2 1, and I have my 2 port. When I am measuring G 2 1, I will apply a voltage to port 1 and measure the open circuit voltage across port 2, and when I am measuring G 1 2, I will apply a current to port 2 and measure the short circuit current through port 1. Okay. And this implies that the voltage gain from port 1 to port 2, and this voltage gain is measured with an open circuit termination, equals the negative of the current gain from port 2 to port 1, which of course is measured with a short circuit termination. Okay. Now, these are all the implications of reciprocity in terms of the 2 port parameters we have defined, but the main use of reciprocity is that, let us say you already know some result, okay, with a particular source. So, let us say this is a network and it consists of resistors, and let us say I have the single independent source somewhere. I will consider that to be a voltage source. Okay. Let us say you already solved for this case, that is, I know that if I apply V 1 here, between these two nodes I get a particular V 2. Okay. Now, what reciprocity theorem enables you to do is, let us say you have an alternative scenario where For instance, let me call this node A and node B, and between node A and B there is a resistor. So, let us say we have an alternative scenario where the voltage source V 1 is replaced by a short circuit, and between node A and node B we have the resistance, and in series with that we have a voltage source. Okay. Let me call that V 2 hat. Okay. Now, I already know the result. When V 1 is applied, a certain V 2 appears across A and B, and obviously you also know this current which flows through the resistor. Okay. So, now let us say you have this scenario or an alternative scenario where I still have a short circuit where the voltage source was, and between A and B I have a current source in parallel. Let me call that I 2 hat, and I want to know how much current flows through this I 1 hat here or I 1 hat in this case. Now, I do not need to solve for this circuit again. I can use reciprocity from this one to get these results. Okay. Because in the first case, essentially what I am doing is I am defining, let us say this is port 1 and this link here is port 2. Then you can think of the original case as the case with port 2 being short circuited. Okay. And this current that I have marked is really the current in port 2, right. I have marked it on top of the resistor, but now the resistor is part of the 2 port. It is really the port current. Okay. So, now clearly this V 2 hat is applied to the second port over there, and the first port is short circuited. So, I 1 hat I can find out without doing any further calculations. It is the same as V 2 hat times the ratio that I had here, which is I by V 1. Okay. I by V 1 would be nothing but Y 2 1 with this as the first port and that as the second port. Okay. Similarly, in this case I can relate this case to the original case by defining something else as the 2 ports. So, let me call this port 1, which is the same as before, and now I will call this between node A and B I define the second port 2. Okay. So, now if you do that, we can see that basically this V 2 by V 1 is nothing but G 2 1. Okay. This port 2 is open circuited here, nothing else is connected there. Okay. And now this is port 1 which is short circuited, and this is port 2 to which this current I 2 hat is applied. Okay. So, again using reciprocity in terms of G parameters, I can find out I 1 hat, and I 1 hat would be equal to negative of I 2 hat times V 2 by V 1. This negative sign comes because G 1 2 is minus G 2 1, and this V 2 by V 1 here is nothing but G 2 1 between these 2 ports shown in blue, and here what I want is G 1 2, that is nothing but the negative of G 2 1. Okay. So, this is the point of the reciprocity theorem. You do not have to be presented with something that is defined as a 2 port network. You could be asked questions like this, that you apply a voltage here and you get something else there, and in the other case you apply a voltage on this side and what response appears on that side. You can use reciprocity theorem by defining your own 2 ports. Okay. And the case in which this can be particularly useful is so let us say we have these 2 points and we are measuring the voltage. Okay. And then we have only resistors in this circuit. Let us say we have a number of sources connected, both current sources and voltage sources. let us say this is the circuit, we have multiple sources and we have this output. Okay. Now, you are required to find out the contribution of all of these things to the output. Okay. So, let me call this I2, V3, V4, V5. Okay. So, now we have to find out this Vx from all of these sources. Now, sometimes it could be easier to turn this problem around and realize that the transfer from I1 to this, okay, when all these other sources are nulled, will be the same as from this one to that and so on. Okay. So, now this Vx will clearly be a linear combination of all of these sources. Okay. So, let me call that K1 times I1 plus K2 times I2 plus K3 times V3 plus K4 times V4 plus K5 times V5. Okay. Naturally, because this is a voltage and these two are currents, K1 and K2 will have dimensions of resistance and K3, K4, K5 will be dimensionless constants. Okay. Now, how do we use reciprocity in a situation like this? What we do is we deactivate all these sources, that is, we short circuit all the voltage sources and we open circuit all of the current sources. Okay. Let me define this is I3 hat, I4 hat, I5 hat and this is V1 and this is V2. Okay. These directions are consistent with the two port convention that I have already used and the current sources and voltage sources that were in place. Okay. So, now because in the original circuit this is terminated in an open circuit, I will apply a current source Ix hat and do the analysis. Now, the advantage of this is that we have a single source in the analysis, okay, and this is many times easier to carry out. Now, this V1 hat would be K1 times Ix hat, this V2 hat would be K2 times Ix hat and this I3 hat would be minus K3 times Ix hat, this I4 hat would be minus K4 Ix hat and this I5 hat would be minus K5 times Ix hat. What I did was, I first considered this and that as the two port and used the Z parameter version, then this and that as the two port, used the Z parameter version, then this and that as the two port and use the G parameter version and so on. Okay. So, I get these ratios. The point is, by analyzing the circuit with a single source, I get these coefficients of the linear combination K1, K2, K3, K4, K5. Okay. So, this is the advantage of using reciprocity in certain situations. Now, it turns out that in circuit analysis in particular, you have something known as noise analysis. Every resistor in the circuit, in general any component in the circuit creates noise and you need to calculate the transfer functions from every noise source to the output and multiply that by the actual noise being created to find the output noise. Now, in this case it turns out that it is particularly simple to turn the whole picture around and apply an excitation at the output and find what appears in place of each of the resistors. Okay. So, that gives you the transfer function, which is also the same as the transfer function from the resistors to the output. Okay. And by using this reciprocity, the simulator is able to calculate the noise transfer functions very easily. Okay. So, that is the application of it.